Aloha, everybody. Welcome to another week of Earth Science, and I hope you're all doing well. I wish I was where this background is. I'm not really quite sure where it is, but somewhere in the tropics. Looks very lovely, looks very nice. We're talking about oceans today, so I thought it was appropriate. And I found my grandpa's old Hawaiian shirt too. So let's get in the mood and go see some cool things, shall we? So here we go. Oh, come on. All right, so we're going to be talking about the composition of seawater and sea life today. I have gave me a good excuse to go look and find some of my old pictures from Hawaii. Last time I was there was about 2 years ago, and seeing some beautiful sea life, which is now unfortunately buried in lava in some parts that we snorkeled in. But anyways, so here's what we got to do. Some geo news, a few little seawater properties and sea life ideas that we'll be looking at. So looking at salinity and temperature and density and how that affects the ocean, and then the kind of main types of critters that live in the ocean. And the reason we really care about the life there is because they are a big carbon sink. They use lots of carbon, which is something we want to circle back to a little bit later on when we start talking about solutions to climate change towards the end of the class here in a couple of weeks. We'll also be making a little bit later on a lab video and instructions to show you how to do your lab. And then all of this week's lecture quizzes, lab activities, and all that stuff, that'll be due on March 31st, which is next Tuesday by 5 p.m. So I'm trying to give you a big, long time to work on things, work on it out at your leisure. Oops. And then I'll be online at 5 o'clock on Tuesday and Thursday. I'll send a Zoom link meeting out via email, and it'll be in the announcements on Canvas. So hopefully, if you just need somebody to talk to, want to have some questions, whatever, I'm here for you. If you need resources for your kids, things to do, that's my day job, is finding really good science lessons for folks and making science lessons. So if you need something, if you feel like you've run out of things to do with your family, let me know, and I'll see what I can do to start helping you with that. Let's see here. So the geo news, not too much other than keep on social distancing, get some exercise in, try to stay local. My original thoughts were, oh, let's go to the mountains and get away from people. But apparently, when everybody has that idea, it's not such a great thing, as witnessed by the beaches in San Francisco the other day. Not exactly the best way to present the spread of what is going to be now probably the peak 6 or 7 days of spread of the virus. So keep on doing what you're doing, stay hunkered down, keep your family safe. I went on a walk the other day down the canal, and this is what I was able to see. Was Half Dome from about a mile away from my house. So just at the end of the canal, you can get out there and see Half Dome, which is 85 miles away from Turlock, but we just have a perfect straight view right up there. That helps us figure out what's going on, which is pretty cool. All righty here. And just to brag, we have a pretty cool natural native wildflower garden going on in our front yard right now. Lots of pollinators. It's nice to be able to sit out there and smell the flowers, see the bees, and it's all local native wildflowers, and we don't use the sprinklers. So we are very, very drought resistant. This is the one time a year it can shine. Down there, free oranges too. That was an activity we did. So let's get a little bit started here, and I shall show you what's up. So we're going to talk about the composition of seawater. I expect this is probably going to take about 30 minutes, maybe, somewhere in that neighborhood. And then give you a chance to take that quiz, and we'll go from there. So seawater, basically, it's about 3.5% by weight of dissolved minerals. So what that means, let me get my little lasery button here. What that means is if you take oh, hey, wrong one. There we go. If you had 1,000 grams of water, basically out of that 1,000 grams of salt water, I should say, 965 grams of that would be just plain old water, pure H2O, and then the other 35 grams would be something like dissolved salt, so calcium chloride, which we see, that's what we use for table salt to eat. And there's a lot of other little minor salts that are in there too, with sulfates and calcium and all those other things that come from all the minerals we talked about at the beginning of the year. So when you have those minerals that break down into their constituent components, that's what you get floating around out in the ocean or dissolved out in the ocean. So a couple of things we're going to be looking at that I need to draw your attention to is the word TDS, and I need a quick drink here. And TDS is total dissolved solids. So when oceanographers go in the ocean and they're trying to figure out how salty the ocean is, it's not just calcium chloride. They're looking at total dissolved solids, so all the things you see over here on the right-hand side, to figure out just how salty the ocean is. And so sometimes the saltiness or the salinity of the ocean actually doesn't measure salt, but for the most part, that's what it normally is. So it's really measuring the total amount of solid material dissolved in the water. It's normally reported out in what we call parts per thousand. So you're familiar with what a percentage sign looks like, right over there. Parts per thousand sign looks very much like a percentage sign with an extra zero down at the end. So instead of saying parts per hundred or percent, we're talking about parts per thousand. And so the average salinity of the ocean is about 35 parts per thousand, or about 3.5% salt in that saltwater solution. And like I said before, the major constituent is sodium chloride. So here's a really cool map, and if you follow the link down at the bottom, you don't have to, it's not a requirement. But if you follow the link down at the bottom there, what that'll get you is all of these maps starting in, I think, 2012. We have satellites that orbit the Earth that can get a pretty good idea of what the salinity of the ocean is based on satellite signatures, which is, I mean, think about it, based on the return of the wavelengths bouncing off of the Earth and hitting this little satellite, they can basically calculate what the salinity of the ocean is. So it ranges anywhere from the low end of things at 33 parts per thousand, or what will be about 3.3% salt. That's those purples that you see. And then it ranges all the way up to some really the hot spots that are almost 3.8% salinity, which is very, very, very salty, or 38 parts per thousand. So you can take a look at this distribution. It's something we'll be talking about when we talk about currents on Thursday. Interesting distributions. Oops, let me see if I can get this thing to advance here. There we go. All right, so where does the salt come from? That's one of the big questions, right? For the most part, the ocean is salty because rocks either on land or underwater have chemically weathered, and those constituent components weather out, they dissolve in the ocean. What's kind of interesting is the ocean hits kind of a saturation point, if you will, with all those dissolved solids. And once it hits a certain point, chemical balances and chemical cycles kind of keep the salinity level of the ocean fairly constant over time, which is good. You know, there's more salts going into the ocean every single day, which just means in order to keep this ocean not as salty, other minerals have to be forming using those salty stuff coming into the ocean. And a lot of the time, those minerals are being created by little biogenic critters. So the shells, seashells, things like that are being created by the critters in the ocean. So anyways, let's see what we got here. So water is by far the most important chemical weathering agent. That's the thing that weathers the rocks the most. And, you know, we talked about rusting earlier on this year as one of the examples of chemical weathering. But it also happens down, well, chemical weathering also happens on the seashore when ocean waves hit and smash up against rocks and break down those atomic bonds of the atoms. So chemical weathering is one way we can get salts in the ocean. The second way is through outgassing, or gases from volcanic eruptions down at the bottom of the ocean. And so what you see here down at the bottom is a black smoker, a hydrothermal vent. And the black stuff is actually sulfur, a sulfur compound that's coming out of the water. It's very hot. It's like 300 degrees Celsius, somewhere in that neighborhood. And what's pretty amazing about it is it's all these dissolved minerals. And sometimes those minerals basically precipitate out and create those really cool columns growing up. And it can provide the basis of a food chain, like little critters there, like crabs and shrimp and things like that eat, or they eat the bacteria, I should say, that grow around there, and then the crabs and the shrimp eat the bacteria. So as long as those hydrothermal smokers go, those black smokers go, all the life around there will keep growing and keep living, which is good for them. And those are normally found at like mid-ocean ridges at the rift zones where you have lava coming up. And water seeping down into the cracks and hitting the magma that's close to the surface and then bubbling back up as really super hot hydrothermal fluids. Remember though, poor guys, their fate in thousands of years is not good because that rift will keep getting further and further apart. And so if they stay on that same little island of hydrothermal smokers, eventually the heat source will run out, their food source will run out, and it'll go away. Life. Oops. All right, so what are some things that can affect how salty salt water is, or seawater salinity? I'm going to give you examples of all of them here pretty quickly, but basically it's precipitation, runoff from land, icebergs melting, sea ice melting. Those things can make seawater more fresh, or adding fresh water to it. Less salty, if you will. If you want to make it more salty, the things you got to do is remove water. So you can either do that by evaporation or formation of sea ice, which I'll show you how in just a minute. So an example, precipitation. If it rains over the ocean just like this, you're adding fresh water in those areas where it rains. So if you're adding fresh water where it rains, you're making the water less salty. It's like if you had a glass of salt water at home, if you want to dilute it, you just add more water to it, right? Same thing happens in the oceans here. It'll eventually get mixed up and stirred out and things kind of go back to normal, but in that one specific little location here, that water is going to be less salty. If you have runoff from land, so here's a picture of Southern California back from 2005 when they had some really huge storms in Southern California that created massive flash floods. All those cool different colors that you see down in the bottom right-hand side along the coast, that's all the sediment being washed off the shore. But along with that sediment is tons of fresh water. So all of this is fresh water being mixed into the ocean and pushing the salinity down because you're adding fresh water from runoff. And then we have icebergs melting. So icebergs, most people don't realize, those come from glaciers that are broken off. So remember, glaciers are ice that form on land and then slide down, hit the ocean, and when they hit the ocean, they break off and they calve. And then that's how they create the icebergs, and those icebergs float out to sea. So eventually, once those icebergs melt, all the fresh water that's in them mixes in with the surrounding ocean and makes that surrounding ocean less dense because you're adding fresh water from the ice that is melting. And so here's one of the other things, the other ways that you can get water or see the salinity of the ocean to be less salty. And the main way here, or another main way here, is if you have sea ice that melts. People always think, but wait, sea ice, how can sea ice melting make it less salty? And it's because sea ice actually is primarily fresh water. We'll see in a few minutes here that when sea ice freezes, it actually squeezes the brine out, or squeezes the salt out, and makes these really cool crystal lattices of just water. And as the water forms and expands, it squeezes the brine, and it's called brine exclusion. And if this is what it kind of looks like here over time. So you can see in the summer months in the Arctic, there goes the sea ice, and then by about September, it reaches what we call the average annual minimum. That's where it's gotten the most amount of sunlight. It's melted as much as it can, and the sea ice will hopefully start reforming in the summertime, or in the wintertime, once it gets cold again. So sea ice melting makes the water much fresher. Oops, come on. So how can we then remove the water? Evaporation, pretty self-explanatory. If you're in a hot area of the globe where you have lots and lots of evaporation and not very much rain coming back down into the water, you're going to have some saltier bits of ocean because there's more evaporation, more water going out than water coming in. And so you're leaving behind some of the salt atoms that are behind the calcium, the chloride, things like that. Um, when water evaporates, it's just the water that goes. It leaves all the salts behind. It leaves all those heavier atoms behind. So evaporation is one way to remove water from the equation. And then another way to remove fresh water from the equation is this formation of sea ice. And like I was saying earlier, it causes this brine exclusion. So when salty seawater starts freezing, it crystallizes in a special way that actually starts helping squeeze out some of the brine. And there's a really cool thing that can happen. It's called a brinicle. And basically what you're seeing there, the kind of the wavy bits down in the movie playing here, that's very dense, salty brine sinking down to the bottom of the ocean as it gets squeezed out of the sea ice forming. What's kind of cool is that brine is so cold it causes the water around it to start freezing. And if you're a living critter like these guys floating around on the bottom that had been happily eating, all of a sudden the brine comes through, freezes everything instantaneously because it's so cold. Think about making ice cream, right? You need salt and ice to make it even colder. It lowers the freezing point. And so it goes through there and kind of causes, wherever the brine touches, causes everything to freeze up. And these poor little critters basically end up getting frozen to death if they stay on there too long. It's like sticking your tongue on a frozen pole and it can't come out. That's pretty cool, huh? So all that white line there, that's the brine that came through and froze the water. And brine goes down because it's more dense. So what I want you to see here is the ice that's up on top. That stuff is primarily much fresher water than the actual ocean water around it. So, there we go. So just again, to show you again here, the surface salinity in the open ocean ranges from about 33 to 38%. And this picture, I think, was from last month. So there might be a reason why it's hard to get any sea salinity readings from space up in the North Pole and the South Pole. I bet you can think about why that is. All right, so seawater. There's some variations in temperature here over time. And so basically, sea surface temperatures are varied based on where the sunlight hits the earth. The equator gets most of the sunlight, primarily, most of the year, equal amounts of day and night almost all year round near the equator. So that water is going to be the warmest by far. All right. The lower surface temperatures are going to be found at the high latitudes, which are the North and the South Pole right over there, because they don't get as much incoming solar radiation during the year. And even when it's 24 hours of light in the summer times at the North or the South Pole for their summers, the light coming in is at a much lower angle instead of a high angle. And so that the amount of energy being transferred to the land is not as much. And if it's already covered in ice, a lot of that light bounces off. And so we'll be talking about that when we get into climate in a couple of weeks. So here's a good illustration, right? Basically, high temperatures at the surface. And what's kind of cool, though, is that you get a rapid decrease in temperature with depth the deeper you go in the ocean. I don't know if you've ever been snorkeling or anything like that, but if you dive down, or even a deep swimming pool, if you dive down far enough, it goes from warm at the surface to much cooler at the bottom. And that creates something called a thermocline. Warm water likes to rise. It's a little less dense. Cold water is a little more dense. And so the cold water kind of sits on the bottom underneath the warm water. And sometimes if you go deep down enough diving, you'll hit that. It's like, whoo, that's really cold. Just don't do that if you have a snorkel on, because then you might drown or something. But if you're looking at this picture on the right-hand side, what's kind of interesting here is this is the winter time. This is the wintertime scene for us in the Northern Hemisphere because the South Pole is in 100% daylight and the North Pole is in complete darkness. But you notice all those sun rays really, 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 really hit at the equator all the time. Doesn't matter which time of year it is. And then what I also want to show you is if you take a look over here, the red line represents the temperature of the sea, the sea surface. So at the top of the ocean, that's the temperature. Even at the poles, it gets, almost to freezing right around there. And then there's no more sea surface at the poles because it's covered in ice for a lot of the time. So pretty cold, then it gets warmer and warmer and warmer as you get towards the equator, and then further south you go, it gets cooler again. What's really interesting, and I think you should take a look at here, is the salinity concentration. And so you notice the warm tropical oceans where you have a lot of evaporation down near the equator, where you're getting a lot of energy, it's not a very salty place. And so we got to think like, man, why would a place where there's so much evaporation also not be very salty? And the answer is, guess what also happens in the tropics? So you get lots of evaporation, but lots of rain too, and lots of precipitation. And so all of that precipitation near the tropics really helps keep the salinity levels a little bit lower. So we're talking it's about 34.5% salty at the equator. And then if you get towards the Tropic of Cancer, which is kind of right where Baja is, Baja, California, or down by Chile down there, they're still having a lot of evaporation. There's still a good deal of sunlight coming in there. But because of other climatological factors, it's dry. It doesn't get very much rain there. And so you have a net loss of ocean water going out and nothing replacing it. So you basically are making the ocean saltier by evaporating that water and taking it away. And then the further north you go, when you get more rain, you're going to get less and less salty water. It's so pretty cool, right? Let's see here. Okay. This is a graph that kind of shows you what I was talking about just a little bit earlier, called that thermocline. So the thermocline is where you have that warm layer of water on top. So right here, this little layer of water is somewhere about 23 degrees Celsius, which is it's about 70 degrees Fahrenheit, something like that. And as you go down just a little bit, so here's our depth. This is 1,000 meters, 2,000 meters, 3,000 meters. So if you go down about 100, 200 meters, maybe 300 meters or so, the temperature stays fairly consistent. And then you hit the thermocline, and the thermocline is a place where that temperature just drops right off a cliff and gets really, really, really cold. And now if you notice, even the coldest water in the ocean doesn't really get below freezing for the most part. Or if it does, it turns into ice and floats up on the top. So the densest water is right around 2 to 3 degrees Celsius, or even up to 4 degrees Celsius, somewhere in that neighborhood. But you can pretty much guarantee if you go to the bottom of any ocean, it's always going to be that temperature right around 2 degrees Celsius, somewhere in that neighborhood. Pretty darn cold. It just sits there, sort of, but it moves. And we'll be learning about those in currents. So if that's the lower latitude, so this would be like near the equator. If you go to the high latitudes, like by the North and the South Pole, there's no thermocline because it's cold on the surface, it's cold on the bottom. That's a big deal. All right. And it is a big deal. That'd be helpful to explain that, wouldn't it? It's a big deal because there's no thermocline there, but what it does set up is a perfect opportunity for density currents to set up. And I'll show you how to do that in just a few minutes here when we get into the densities. All right, so what's kind of cool about the ocean, if you've ever been there, you can probably understand that the ocean is huge. And if you've ever boiled a pot of water, it takes a lot of energy to heat up that small pot of water, right? You have to turn on the oven or the stove for 5 or 6 minutes to get it to boil. That takes a lot of energy to change that mass. The ocean is the same thing, same way. It has a lot of thermal inertia. So it absorbs a lot of energy before the temperature can kick up or go down. And that's what's kind of cool though, is it can also release a lot of energy before the temperature rises or drops. So it's a good thermal regulator for us. If you live by the ocean in San Francisco in the summertime, you know, when it's 100 degrees in Modesto or the Central Valley, it's only 50 or 60 degrees over in San Francisco because they have the ocean water that is cooling off the air above it and acts like a natural air conditioner. Um, However, the bad thing is if we keep pumping heat into the ocean, it takes a long time for that heat to kind of start registering and be measurable. But what we've noticed over the last 120, 140 years or so, if you look at this graph down here on the bottom, is that the sea surface temperatures have been gradually, steadily rising. And even though a half a degree Celsius does not look like it's all that much, I mean, a half a degree, big deal, right? Imagine how much energy the ocean had to absorb, the whole entire ocean, to raise the average ocean temperature by a half a degree. That is a lot of energy. And that energy is coming from trapped excess heat that we'll be talking about in global warming towards the end of the semester. And that will all be solution based. So we'll see a few problems, but then hopefully give you something to think about that's good and positive and can change the world for good once all this craziness is over here. So global warming is definitely influencing ocean temperatures. So temperatures are one thing that affect seawater. And then another thing that affects seawater and how it eventually starts moving is its density. And so the density we've talked about with rocks, with granite being less dense than basalt. Density is just basically, you know, the mass per unit volume, or D equals M divided by V over there on the left-hand side. What's really cool about density in the ocean, though, is density determines the vertical position in the water column in the ocean. So if you have less dense stuff, it stays on top. And if you have more dense things, it stays on the bottom. So over here on the left, I have some styrofoam pellets. That's a representation of something that's not very dense, not very much atoms in a space, versus lead, where you have a huge amount of atoms and mass of those atoms stuck in a small space, which makes it super heavy. So just to give you an idea of something really cool you might want to do with your family at home if you're stuck and bored, you can do this quick little saltwater density experiment. I don't think you need safety glasses though. So basically you just need some salt if you can get your hands on some salt at the store. You can see all the instructions. Teaspoon measure, cups, color fizzers, or just basically food coloring. And so you add 1 teaspoon, 2 teaspoons, 3 teaspoons, and a whole bunch of teaspoons to all the different cups. And then you put about 9 ounces of water in each of those cups, stir it up, put in the colors. And then if you have a clear straw, which you can get at the dollar store pretty cheaply, check this out. He starts in the end that is less dense, lets up his thumb a little bit. And if you notice, the things that are less dense keep getting pushed up and up and up. So if you click the link down there on the bottom on the PDFs, once you get this and download it, it'll take you to this website. And there's lots of other experiments that you can do with this setup. So if you're looking for something fun to do with your family, there you go. And it has to do with density. Oop, come on. So here's the point, right? Less dense things float, more dense things sink. And this is going to be the impetus for how we get ocean water to move on a large scale over big, huge, long time periods. And so there's a couple of things that affect the saltwater density, right? Number one is the salinity. So how salty is it? Things that are more salty are going to be more dense. Fresh water is less dense than salt water. However, It turns out that temperature is the greatest influence on density, all right? Temperature is the greatest influence. So hot water is way less dense than fresh water, and hot water floats, cold water sinks, like I was telling you with that thermocline. So I just want to show you this. Here's a salinity experiment to show you what happens when you have two different types of salinity mixed together here. So obviously we have some blue stuff on the bottom, which must be more dense because it's on the bottom. And we have orange water on the top, which is probably not very dense because it's on the top. So let's see what happens when we pull this middle piece out of the top right here. It's super exciting. So he's going to just pick it up just a little bit here. And if you notice, the dense blue stuff goes over and pushes underneath the less dense orange water. And then the orange water, whoop, since it's displaced and needs some place to go, kind of slips out underneath this side and comes up and matches it equally over there. And if he takes the whole thing apart, interesting. So you can take a look at some of your own density YouTube videos if you need. But the heavy stuff, dense stuff sinks, the lighter stuff floats. And that can create big movements, as we'll see here in the ocean currents. Oh, I know what I want to mention. So, come on. So once we got this little orange and blue layer here, where that line of sharp differences in density occurs, we have a special name for that. When we talked about temperature divisions, we said that was a thermocline. But when we talk about density divisions, we call that a pycnocline. And so a pycnocline is basically where the density changes super rapidly, where you have very not dense stuff on top and way more dense stuff on the bottom, all right? At the high latitudes, we don't really have a huge, massive change in density with depth because the water is already cold. And so when you get to the poles, the water is already cold and it's already sinking all the time. And that's how we get our nice little density currents going on up there. It's way colder than, let's say, at the tropics, right? Where it's super warm and super hot. So the thing you need to know here is that this is the pycnocline. This is where density increases greatly with depth, all right? So the fresher, warmer water would be on top. The more dense, colder water, sometimes saltier water, would be on the bottom. Pycnocline, fun word. All right, so because of the thermoclines and the pycnoclines, we actually have a couple of different layers in the ocean that you should know about. And that's called the surface mix zone, the transition zone, and the deep zone. And so that surface mix zone is anywhere from like 300 to 400 feet deep. Excuse me, I need a drink of water. The surface of the water up there, it gets mixed by winds and waves. So that's why we call it the mix zone. So wind and wave and tides, it's just all mixed together quite a bit. It's pretty uniform temperature all the way throughout, and it makes up about 2% of the ocean is that surface mixed zone. Then we have what we call this transition zone. And if you notice, what's kind of interesting, it's like this dip. It's not perfectly flat all the way across. So we'll figure out why that dip exists here in just a quick second. But in this transition zone, it's the zone that separates that surface mix zone from the deep zone. It's about 18% of the ocean water exists in here. And this is where you find your thermoclines and your pycnoclines are in this transition zone right in there. So why do we have this funny bulge of the deep zone where it's the sunlight never reaches, where the water density is super constant and high? It's 80% of the ocean. So why does it bubble up right there? Well, part of it, hopefully, if I can draw, let's see here. Because at the surface, if you have cold, dense water at the poles or near the poles, they're going to tend to go down. And that cold, dense water is going to be moving, moving across the bottom. And when it hits the middle, you basically have these two pieces of cold water coming together, and they have no place else to go when they collide except up. And so as they come up, it creates a little bit of a bulge. So that's our first little bit on these density currents that can be created out in the ocean. So the deep zone makes up about 80% of the ocean, and the reason you have this little bulge right here is because you're getting this cold water pushed up at the equator from the pole. So it's kind of weird that if you go to the tropics, you don't have to go down as deep to hit the deep zone as you would, let's say, if you lived in San Francisco or off the coast of San Francisco to get through the surface in the transition zone. It's a lot thinner there because you have the big plume of cold water being pushed up. Of note, that layered structure does not exist near the poles. Just always cold water. Come on. Oh, I guess it helps if I take off the arrows, doesn't it? All right. Let me erase my arrows here really quick. All right, so the ocean has lots of life. I don't really want to spend too much time on the ocean life here, but the things you need to know about ocean life are this. Life grows best where there's light. All right, sometimes you get some little critters living by the hydrothermal vents and things, but most of the food chain that we depend on and that the earth depends on happens at the surface with photosynthesis. So that photosynthesis happens in what we call the photic zone. That's basically the part where light can get down into the ocean. And then the euphotic zone is the place where photosynthesis is really taking off. And so I'll show you some of those a little bit later in just a couple of slides here. But my intent is not for you to memorize every single bit of this, other than the fact that the deeper you go, less light gets there. It becomes pitch black. The light gets filtered out. And I want to show you where life is most productive in the ocean, because that's going to play a big role in like sustaining our fisheries and also trying to find a way, if we want to help fight climate change, you know, which parts of the ocean are going to be doing the most good by taking carbon out of the atmosphere when they photosynthesize. Let's see here. Spotlight. Oh, next slide. There we go. All right, so there's a couple of classes of critters that you need to know about. The first one is called plankton. And so plankton are just these things that float along. So they cannot swim across the ocean by themselves. They just float. So here's a human hair for scale. There's 2 millimeters for scale down there. Basically, phytoplankton are plants. These are algae that photosynthesize, and then they float along through the ocean, drifting on the currents. And then the zooplankton are little animal critters that are too small to be swimming against the ocean currents. And so they are at the mercy of the currents of the ocean being drifted and blown across or drifting across the ocean of the earth. And so it's kind of crazy is most of all the biomass, so all the mass of all the living things on earth, think about trees and plants and humans and bugs and all that stuff, most of Earth's biomass is actually in these microscopic critters that live in the ocean. It's kind of mind-blowing, right? So those are called plankton. Floaters are plankton. Things that swim are called nekton. And so anything that you can think of as swimming that can go against the current independently, that's what we call a nekton. So sharks and whales and fish and squid, all those things. And then we have the bottom dwellers, which are called benthos. And so there's a huge number of species that exist on the shallow ocean floor, like in coral reefs. Sometimes they live all the way deep down in perpetual darkness and deep water, but like the black smokers here. But if you live on the bottom, you crawl on the bottom. That's what we call a benthic organism or benthos organism. They live down there on the bottom. So like I was saying earlier, the photic zone, that's where light is coming in. Basically below the photic zone, it's called the aphotic zone. No more light can get down through there. It's filtered out. You can't see anything. So if you've ever seen a movie of like, well, not Jaws, what was The Meg? I haven't even seen that one yet. But if you've seen actual documentaries where folks dive down deep into the bottom of the ocean, they need to bring lights with them. And the submarines have to have lights because the light does not get through, the sunlight does not get through that far, maybe a couple hundred meters below the surface. All right, and the euphotic zone, that's where photosynthesis is really like kicking. So another thing that affects the type of life and the life zones that live in the ocean is how far away they are from shore. So if you've ever been tide pooling, that's called the intertidal zone, where the tide comes in for part of the day and goes out for part of the day. It's where you find like sea anemones and things like that. The neritic zone, that is basically the area that's close to shore, and then you have the oceanic zone, which is way far off, deep out in the deep ocean. You don't need to know too much really hugely about that, other than the fact that you're going to find most of your life is blooming really good in that neritic zone, closer to the ocean, or closer to the edges of continents and islands and things like that. The water zone can also, the depth can also affect the types of life. And so we have pelagic, benthic, and abyssal zone. So if you live out in the abyssal plain, it's a pretty lonely existence out there. Excuse me. It's deep. The water pressure is super high. Temperatures are super cold, right? Just barely above freezing. No sunlight, not much life. And your only food is decaying particles from the surface that sink down to the bottom. And that's what you get to eat. Dead whale floating to, sinking to the bottom of the ocean. Super awesome. All right. So last little bit here, and this is the more important part. I'm okay, I promise. Is ocean productivity. And so productivity is, if you think about the ocean like a farm is way more productive when more plants are growing there, or more pigs or more animals are growing there. So productivity is a measure of how much stuff is actually being grown. And on Earth, we get most of that energy to grow things starts with the sun and the photosynthetic stuff that grows. So if you have little small organisms that grow, then you can have bigger organisms that eat those smaller organisms, and even bigger organisms that eat those medium-sized organisms. And so we call that productivity. The photosynthetic critters, we call that primary productivity, because without them, nothing else would survive. Something has to be able to transfer that sunlight and photosynthesize it and turn it into sugars and living things in the body. It also happens to be that these little critters, these photosynthetic critters, they also store a huge amount of carbon. They need carbon in that photosynthesis to, remember they take in carbon dioxide and give out oxygen. They sequester tons and tons of carbon, which is really important for our future. So let's see here. So the sources of energy for those blooms can be photosynthetic. Sometimes it's chemosynthetic if you live by that, down by those black smokers at the mid-ocean ridge. But the thing that influences plankton or these primary productivity has to be the nutrients. So how much nutrients is in the water beyond the sun. So you can have the sun, but if you don't have other chemicals and nutrients in the water, you're not going to be able to grow. And then the amount of solar radiation. And so here's a really cool little drawing that shows you just how much energy it takes to keep us alive. So for every 500,000 units of sunlight that come into the earth, about 10,000 units of that energy are actually converted into biomass by these little zooplankton and phytoplankton, basically. So these are the photosynthetic critters here. So think about that. That's a 98% loss of the sunlight's energy going into making that. So from that 2% that survives, then the zooplankton eat the phytoplankton, and they're about 10% efficient when they eat that. So that's another 90% loss. So of that original 500,000 units from the sun, there's only 100,000 units of energy left, which then becomes 100 units by the small little fishies that eat these zooplankton, which then comes 10 units. So think about that. This tuna, for every fish that he eats, for every 10 units here, that he gains, it took 500,000 units of the sunlight energy in order to give that one 10 units. And then we go out in a boat, we catch it, we eat it, and look at this. 1 unit becomes trophic level 5, or what we call the top of the food chain here, right? So that's a lot of loss over time. So 400, it took basically a loss of 499,999 energy units from the sun to be able to get us the energy we need. So it's a good thing there's lots of stuff growing in the ocean, because if there wasn't, it wouldn't be able to support our life, which would not be good. So where are the oceans most productive? Where's the productivity happening? Well, if you look, the polar regions, they have a really productive time right around the summer. And that's because you have all these nutrients rising up. It's called upwelling, which we'll talk about next week. But you have tons of nutrients. However, there's not much sunlight up at the poles, near the poles during the winter time, and so not much can grow. You need the sunlight is the big stuff. So they have a lot of nutrients, but not much sunlight. But when the sunlight hits, look at that. And so this is why the whales, these pictures I took in Alaska last year, the whales swim up to Alaska and up north because in the summertime, because there's such huge, massive phytoplankton blooms that they can then go feed on, and it supports herring and other fish that these guys eat. So that's pretty cool. So polar regions are super productive, but only for a short amount of time. The tropical oceans then, they do not have very high productivity at all. That's the orange line over there. And basically the reason they don't have much productivity is they have a lot of sunlight, but even though they have a lot of sunlight, they do not have a lot of nutrients. The thermocline prevents upwelling from happening, just kind of keeps a lid on that water there. Kind of like on a smoggy day in Turlock when the air doesn't circulate, the same thing happens in the ocean. So no nutrients can get up, and if you're away from an island and just out in the middle of the open ocean, the tropics are really not a good place to have a lot of productivity happening. Just there's not enough nutrients happening. However, you get closer to shore, then there's enough nutrients, and that's where you get the coral reefs and all those big things. But they disappear pretty quickly the further away you get from those islands. So the temperate oceans would be places like where we live, San Francisco, San Francisco to Oregon, and on the East Coast. And basically, these are the most productive oceans overall. You don't have the hugest spike like we do in the polar regions, but we do have a pretty good boom. And it's pretty consistent throughout the year because, well, in the wintertime, you have low productivity because the days are short and the sun is low. So not much nutrients. Well, I should say they have a lot of nutrients, but the sunlight is low, so it's not very productive. Then in the springtime bloom happens because the sunlight starts popping again. And as the sunlight starts popping, it causes all that photosynthesis to go. And once the photosynthesis goes, a lot of that productivity, those things that get created, things that are photosynthesizing, they get eaten pretty quickly. So the bloom starts going down a little bit, A, because they're getting eaten, and B, in the summertime, when you have more energy hitting the surface of the water, the surface of the ocean starts getting a little warmer and it develops a thermocline. And so when you put the thermocline on, not as much nutrients can also get up to the top. So it starts, the productivity starts going down again. Let's see here. Yep. So in summertime, the thermocline happens. No nutrients can get to the surface. Productivity goes down. But then when the fall happens, in the fall, the thermocline starts breaking down. The ocean surface starts getting cooler. And as it starts getting cooler, it breaks up the thermocline and it starts circulating again. A little brief bit of nutrients comes to the surface, and then you get kind of this really small, short-lived fall bloom of phytoplankton, which all the critters in the ocean love again before the sun gets too low to be super productive for the rest of the year. And again, that's one food chain. And one last thing to quickly note before we go, just in case you're not familiar, a food chain is like a straight link to go from like diatoms, which are the photosynthetic things, to a copod, to a herring. A food web shows you all the different paths that this thing could get going. So a diatom is like a little plankton here. And how's it to get to a herring, which is a fish? Well, it could either be eaten by one of these things, or it could be eaten by one of these things, or these things, and then the herring could eat any one of those. So this is a food web. It helps if you have a food web to eat stuff because it gives you a lot more choices. If, for example, if this North Sea herring only ate amphipods and the amphipods for some reason had a bad year, it wouldn't be able to eat anything else and it would starve. So that's why it's good to be a part of a food web and not just a straight food chain. So anyways, I think that's that. All right, there's a quick quiz on Canvas. It's 10 questions. It's pretty easy to do. Get that submitted to me, and then you can start your lab. Thanks.